Hey, that popped up faster than I thought. Welcome to Organic Chemistry Wednesday edition. And let's zoom on over to the other screen. And here we go. We've got a test next week. We have lecture notes from Monday, that's 2 days ago. And that tells us what material is on the test. We're going to continue with our discussion of the last few segments that we haven't covered yet today. We've posted them. The layout's been posted in Moodle where test one materials are located. If you haven't been there yet, please go there as soon as you can. Look at the document at the bottom of the screen. It goes question by question. What questions you will see on a test based on an old test. There will be no surprises. Okay, the test one problem set is designed to get you ready for the test, and it's got questions similar to the test. Some of the questions are a little more difficult because you can spend a little more time with them. But if you want to know exactly the level of difficulty for your test questions, look at the old test you're told to look at, then find the same type of question on different versions of test one in older tests. You have more than 10 old exams to work from. Reminder, always start with the most recent one. I caution you against using COVID-20 tests. So when I say start with the most recent one, let's pretend winter 20 didn't happen and always start with the previous semester, fall 19. Go through all of those questions, then go back to the one previous to that, go through all of those. You'll start to see I always ask the same questions over and over again, and you should expect to see them as well. Okay. We're going to do a problem set this weekend. This is brand new. We haven't had a test one problem set ever, and that's going to be dropping, as you guys like to say, Friday at 8 a.m. It's actually probably going to be there earlier. So if you want to get a head start on it, it may even be sometime late Thursday or maybe even the middle of Thursday. I don't know. I'll try to send an email reminder to everybody as soon as I post it. Judging from the content on the problem set, if you've finished your studying and you start the problem set, it'll probably take about 2 hours. If you have not started studying or only studied partially, then you're going to have to be learning as you go. I mean, ideally, that's not the best way to do it, but it's not going to hurt your outcome on test one problem set. It's just going to make you have less time to study after you've finished the problem set before Wednesday. Tomorrow afternoon, there'll be a new sample lockdown exercise, because for you to access the test when it's available, you're going to have some software on your computer. Some of you might have it from other courses already, and some of you may not. All you have to do is follow the instructions, and it will prompt you as you go to say, it looks like you need this software, and it will take you towards it, and it'll get your computer ready. Make sure it's the computer you're going to be using Wednesday. Okay, you'll have until Monday to get that done. This is not a major exercise. It shouldn't take a long time. And next Monday is all review all day, and you are in charge. I would like to see you email me specific exam problems that you would like solved before Monday. That way I can organize things, and if a lot of students are asking, the same exact type of question from different exams, I'll pick which one I think is most suitable for you and do that problem. And I would need some details like which semester, which part of the exam, they're very clearly labeled, and exactly which question. I have a confession. I didn't look at Fall 17 to come up with this example. There might not be a 3B in Part 4, but that's the kind of stuff I need. What semester, what part of the test, 1, 2, 3, 4, and which question in that part. So have that have me, as soon as while you're studying and doing the problem set and you're finding exam type questions that seem to relate to the test layout that I've posted, and you're having a little trouble, look for an old question. We'll do it together on Monday. All right, without much further ado, there's one more thing you're going to have to do. I'll be sending an email saying, I may have sent it already. I'm not sure. It may be in the study guide. I need you to tell me which exam you want to take. There's the morning option and the afternoon option. They're on the syllabus. The exam times, you have to pick one. I will not let more than 25 students sit for either of the sections. So it'll be the first 25 students requesting to sit for one of the sections, and after that, you're going to be in the other section. So if you have requirements in your scheduling that prevent you from making one of those sections, you better get your request in soon. So just go straight to the syllabus. It's got the exam times on it, and email me saying, I need this exam time for test 1. All right, we're going to move on and finish up our discussion of chapter 2 today. The chapter 3 material, we've already dealt with the little bit in 3 that we have to. And in chapter 2, we're going to talk about redox reactions in organic chemistry. And you're going to have to tweak your definition of oxidation and reduction that you learned previously for very good reasons. In organic chemistry, carbon does undergo redox reactions. Proof of that is that oxidation and reduction potentials, you studied redox potentials, and it was a nightmare, you balancing the redox reactions and coming up with redox potentials after that. You do not have to do that in this course. That's good news, right? But the bad news is you can't use your old definitions, because your old definitions would say that carbon doesn't participate in redox reactions. Your old definitions would say such thing as a fuel cell does not even exist. We have fuel cells that are going to be put in cars soon, where we don't burn the fuel, we trap the electricity that results from the reaction that's the equivalent of burning it. Just like you don't burn food inside your body, but you do get the same energy out of the food that you would have if you burned it. Okay, so there's redox reactions going on, and we have to acknowledge that carbon never loses electrons. So you can't say my definition is losing of electrons is oxidation, not for carbon. And you can't use your old definition of gaining of electrons is reduction, because carbon's never going to gain electrons either. The best we're going to do for carbon is either have electrons move further away or move closer to carbon in bonds. So I like to start with a combustion example, and section 2.6 is about combustion. Whenever I re-edit the book, I'm gonna combine combustion into redox, because they are the same. Combustion is just a very small example of a redox reaction in organic chemistry. Anyway, a lot of talk. Let's look at what's happening. This reaction has a redox potential, therefore oxidation and reduction have to be happening. Carbon starts off with only bonds to hydrogen. You can see that, right? I'm only going to ask you one thing. Where are the electrons in that bond? Are they closer to carbon? Are they closer to hydrogen? Or are they exactly halfway in between? All you need to do is use your definitions of electronegativity, and you say, okay, on average, the electrons are a little bit closer to the more electronegative carbon and a little bit further from the less electronegative hydrogen. Okay. When this reaction's over, carbon is bonded to oxygen. Here it is with CO2. Oh, in case you haven't studied this yet, you always have to have a fuel in a combustion reaction. In this example, our fuel is methane, CH4. The other reactant must be oxygen. You can't have fire without oxygen. And the two products, we're always assuming we have a good, complete, clean combustion reaction. The two products are always carbon dioxide and water. In the winter, you can see the water coming out of the tailpipe in your car because you live in Michigan and it's cold. And the steam that comes out condenses and you see little water droplets in the air. You can't see the CO2 no matter where you live. Maybe on, let's see, what's the coldest planet you can think of? Mercury. You might see CO2 there. Okay, so in this reaction, the electrons, did they get closer to carbon or further away as this proceeded? I think the diagram shows it clearly. From carbon's perspective, electrons are moving away. Now you can go back to your 141 definition or whatever course you took at another institution and say, ask yourself, does that sound like losing or gaining when the electrons get further away? Isn't getting further away on the way to losing electrons? So carbon's becoming oxidized because the electrons are moving away from it. Now, in terms of oxygen's perspective, oxygen started with the electrons exactly halfway between the two oxygen atoms. And I know there's 4 electrons in here because it's a double bond, but I'm just looking at any of the individual bonds here. And when you're done, there's 2 fates for oxygen, as you can tell. Oxygen ends up with carbon in carbon dioxide. And in that instance, they got closer to oxygen. Does that sound like the electrons are reduction or oxidation for oxygen's perspective? Did the electrons come closer or move further away to oxygen? They got closer. That's like gaining electrons, isn't it? So we say oxygen got reduced. Same story when oxygen ends up in water, except they get even a little closer, but the gist of it is the electrons, if they go cross halfway or start halfway and go towards one atom, they get closer to that atom. What do you call it? You call it reduction. Oxygen is undergoing reduction. Oxygen is becoming reduced. And above, that's a D. And above, carbon is becoming, well, the electrons are going away. If they kept going away forever, they'd be lost, right? Well, just think about the direction. The electrons are going away, going away, going. If they're lost, that's oxidation from your old definition. What's on the way? Moving electrons away. So carbon is becoming oxidized. And we also talk about agents. Cause other atoms to become, there's 2 agents out there, aren't there? One, reduced. And not surprisingly, that's called a reducing agent. Agent. And some agents cause other atoms to become oxidized. And we call that an oxidizing agent. Okay. Let's do these in green highlighter. Or some kind of highlighters. Highlighters, they're here. This molecule caused carbon to become, it's already written on the right side of the screen. What happened to carbon? What did it become? Carbon is becoming oxidized. That means the other molecule that's not here caused it to happen. This molecule caused carbon to become oxidized. Summary. O2 is the oxidizing agent. If O2 was not there, carbon would not have become oxidized. Flip the script. Let's talk 2 seconds about hydrogen. In hydrogen here, the electrons started closer to carbon, the other atom. In the end, the electrons are still closer to the other atom. Did those words change? They did not. Hydrogen didn't undergo oxidation or reduction. So that's the end of hydrogen's story. They stayed left of halfway for hydrogen here, and they end up left of halfway here. So we're not going to talk about hydrogen here. It's carbon and oxygen. Okay, the other molecule. This molecule, what did it cause oxygen to do? This molecule I'm having trouble with ease here. Got to slow down. Caused oxygen. What happened to oxygen? Look at the second sentence over here. Oxygen is becoming reduced. Well, this molecule caused it to become reduced. What's the conclusion? CH4. Notice we named the whole molecule for agents. CH4 is the reducing agent. Now, when we're trying to study these notes and it's not a video, where did we start today? We started with these pictures. Asking ourselves, what happened to the electrons? Then we came up with these conclusions. When electrons get closer to an atom, the atom's becoming reduced. Electrons got further away from carbon, carbon is becoming oxidized. Those are our new definitions, by the way. Electrons moving further away is oxidation. Electrons moving closer is reduction. Can we put that into sentences somewhere? You've got mnemonic tricks from 141, depending on if you had Dr. Yackel or Dr. Buchanan teach you, or some similarly minded teachers. They like different words. We need new words because those words don't work anymore. Let's use this one. Moving electrons away is oxidation. Moving electrons away is oxidation. And let's make that, oh, those are supposed to be electrons. Our symbol for electrons is E with a superscript minus. And there we go, bold and red. And copy and move it. Moving electrons away is oxidation. That's our new one. Yeah, I'll put it over here. Organic chemistry. And what about the reduction? Moving electrons closer is reduction. Electrons moving Electrons moving electrons away. Nice English there. I guess I didn't want that dash was just a dash. It wasn't supposed to be an electron symbol. Can I get in there? Can I? Can I? Is it gonna let me? It's always a battle. Someday I'll figure it out. There. Can I get back here? Because I got to change this one. There. Moving electrons closer. Closer is reduction. Moving electrons closer is reduction. All right. So they're not the greatest mnemonic tricks like oil and rig or Leo says grr. But I mean, if you got a good imagination, what animal makes the noise meow? A cat. Can cats spell? No. So you could spell meow, M-E-A-O. And there's an Arab word that relates to somebody being like a sneaky or a tricky person, makar. It looks a little like this. Okay, it doesn't look at all like that, but you can, in your imagination, you know, a homonym. Moving electrons closer is reduction. Those are our new tricks, memory tricks for organic chemistry. Organic chemistry, we need new definition. Organic chemistry, we got to use these definitions because that's the best we're going to do. And next up, I don't know if we'll do it in this segment. This is a good logical stop for this segment. We're going to actually assign redox numbers. And we're going to get rid of all the exceptions you had to learn for redox numbers in 141. They're going to go away. You just had to memorize them. They never tried to explain them. No, I know them. When you're first learning chemistry, there's only so much you can handle. But when we come up with our new definitions that give us oxidation numbers based on bonds, there will be no exceptions. So you can figure out that a peroxide oxygen should be -1, and you can figure out that other oxygens like oxygen and water should be -2. So look forward to that in about 5 minutes.